Thank you very much. I would just like to start from a precise day in the past. It was the 2nd of October of 2006, and one of the most important contests in the history of data science was about to begin. Netflix, which was at that time a semi-unknown DVD rental service, was offering $1 million to improve their movie rating algorithm by 10%. In the following 2 years, some of the biggest names in the machine learning community joined the contest. For example, Geoffrey Hilton and researchers from Google, Yahoo, and so on and so forth. Finally, in September 2009, after almost 3 years of contest, the prize was finally awarded. As per the rules of the game, Netflix was handed over the code. And finally, this code was just thrown away. It never made it to production. Why did it happen? Well, it was just too complex to achieve real business value. Right now, lots of academic researchers are applying machine learning techniques to the energy world. Unfortunately, many of these models, many of these approaches may still fail to deliver real business value. And engineering complexity is just one of the reasons why it may happen. Let's say, for example, this use case. It's short-term power forecasting. Right, so the traditional setting is like this. We suppose that historical load data are available until 24 hours before the moment to forecast. We also assume that weather data are available until the moment to forecast. Unfortunately, this is not how it works. In Italy, for example, there is a 2-month delay before actual real consumption data become available to energy provider. I mean, 2 months is just an average, a simplification, but it's not that easy. For example, for industrial customers, you can pay lots of money, actually, to get data with a lower gap. And in other European countries, it is even more complex than this, but the problem is still there. Basically, you have no recent data about your load demand. What are the consequences of this? Well, they are pretty severe. Basically, you cannot use any ARIMA-based model. We have shown experimentally that neural network-based models, for example, RNN and LSTM, they lose their effectiveness. Of course, there are solutions. For example, you can use a first Fourier analysis to model the, let's say, low-frequency components of the series. And maybe you can use Lasso, as it was done by Alessandro Incremona and Giuseppe Di Nicolao, to select the relevant harmonics. Or you can use embeddings and maybe work on two different time scales. For example, you can use embeddings from recent data for weather and embeddings from last year for load. At the end of the day, if you do like this, either you use Fourier analysis or you use embeddings, you have to frame your problem as a regression. Basically, you cannot use a time series-based approach. Right. No matter how hard you try, there is no model which is able to compensate for the lack of information due to the unavailability of recent data. Let's consider another example now. Short-term gas demand forecasting. This is a scatter plot based on Italian gas demand, only for residential sector. It is pretty evident that the weather and temperature in particular is one of the main driver of gas demand. This is because in Italy, all the regions but Sardinia rely on natural gas for domestic heating. So we can say that from roughly 18 degrees upwards, there is no effect of temperature, and below 18 degrees, actually the optimized threshold would be 17.3, but below the threshold, basically the interaction is linear. Right, but which temperature are we talking about? Most of papers do not even address this issue. I mean, you can use two kinds of temperatures, the actual ones measured and the forecasted ones. Some papers use the actual temperatures both to train and predict with the models. In the real world, in a real context, in a company, you have no choice. Either you're God, which is pretty unlikely, or you have to use forecasted temperature from weather services. What's the impact of that? Well, based on probabilistic models, we derived a formula which relates the root mean square error on temperature forecast to the root mean square error on natural gas demand forecast. It is a pretty easy relationship which starts with this, let's say, almost flat curve, and then it becomes linear for bigger errors. You can find the precise math in the papers. Well, where are we in terms of real errors? From the provider which gave us the data, it's about 0.25 Celsius degrees, so it's pretty low. Is this model accurate enough? We designed a simple test, and it works like this. We took lots of models. For example, neural networks, you have KNN over there. You have super vector regression, random forests. Basically, each point in this chart is a different model. And we first trained and tested the model with forecasted temperatures. Then we train and test the same model with actual temperatures, and we transform the root mean square error with our formula. You see that basically the two figures almost perfectly agree. So this error propagation model is somehow good. You might argue, right, but the increase in forecasting error based on temperature error is monotonic, so why should I care about using actual temperature or forecasted temperatures? Well, first issue is this model may be good, it's not perfect. For example, you can see that point there, which is pretty detached from the 45 degrees line. The second issue is that if the error in temperature forecasting is big enough, you just have better to drop temperature forecasts from your model and let the model learn an implicit forecast of temperature based on the behavior of the time series. This can be proven by just experimentally. To conclude, academic research and business research have two different purposes. The first one aims at creating tools, and it would make little sense to test a brand new model of an overcomplicated realistic scenario. But it would make little sense also to hope from a business perspective to just dive into the literature and find a ready-made recipe for your problem. So both kinds of research are equally important. What I would like to leave you with as a last thought is that these two kinds of research do not still get equal attention from the community. For example, in scientific journals, it is very rare to see a real use case of some machine learning technique. Maybe in the papers by Google or Yahoo, but not, let's say, in standard literature. This is why events like this one, or initiatives like the one from the journal Applied Stochastics Models in Business and Industry, which, by the way, is not really about applied models, but it's more about models, are so important. Because if these two words do not come together and share challenges, experiences, and results with each other, so much value is lost. You will be able to find these slides online. You will find all the math and all the results in the papers. And I'm Emanuele Fabbiani. You can get in touch with me with this very great Tinder-like application, or you can find me on LinkedIn or ResearchGate and whatever. And I thank you very much for your attention.